Hey everybody, welcome back to Fastware. Thanks for watching. And today I have a interesting discussion on the constructors and destructors in C++. It's sort of a fundamental thing in any C++ application to have constructors, destructors. It fuels all this discussion around RAII, resource acquisition is initialization, to construct the destructors to clean up the behavior. However, today so these are the main benefits of C++ constructors, but I have a slightly different topic in mind. It's the performance of C++ constructors, and if you're performance bound, how to overcome some of these problems that C++ constructors and destructors present. So this is going to be the main subject of today's video. So as usual, I have a little benchmark of constructors, destructors, small. We have a complex small object, and then we have the complex medium object. And these complex objects are very trivial. So a small one has a 4-byte integer. Then you have 16 integers representing 64 bytes. Then 32, which is 128 bytes. And then 64, which is 256 bytes. So you have 4 different types. And using constructors and destructors, you basically create your object. You make sure that your values are not optimized away since they're not being read back. Compiler will be very happy to go and just remove that initialization altogether. So not to do that, so we optimize it away. Destructor will be called as we close our braces here. The clobber memory ensures that destructors are called and written to. So the constructors take all the values that we have from 1 to 64 and write 1 in them, and destructors write 0 in them. As you can see in my example, which I have the simple init implementation. So what we have is we fill our arrays, in this case 16 elements, from 0 to 16, from 0 to 15 with value 1 as our initialization. We do exactly the same thing. We do not optimize these values. And then we write zeros into them and club with the memory. So this is all there is to it. So what I want to demonstrate is run a little benchmark, which I have. And we have some performance characteristics at different scales as usual, because problems scale differently and we want to understand the general behavior, not the idealized behavior of what we're trying to benchmark, right? So at certain scales something can be very good, but when you move into a different scales it might be terrible, and this is what we want to avoid, that bias that we can introduce. So here we ran some benchmarks, and as you can see, for small constructor destructor behavior, we have about 197 nanoseconds to run 100 of them, and for the simple init it's about 25.5 nanoseconds, right? So that gap between the C++ constructor destructor, the time it takes to do that, and the small init, which just initializes an integer, this gap represents your program doing nothing. Your program wasting time, literally, as it accomplishes nothing in between that time. And we can actually look how this scales. So as I said, a small object is a single integer, then 16, then 32, then 64 for the large X examples. And let's pause through and have a look at the large X examples. So at large X examples, our simple init is about twice as fast, not as big of a gap as it was initially, but it is still twice as large. So I have prepared a little Excel. So let me just transition into it. So we have transition into it. There we go. I hope that should be visible. So here first I just took that data, put it appropriately, and then plotted it out to see what kind of different situations and what kind of how the graph looks in general. So taking these values, so this is our constructors, destructors, and you can see at the 10,000. So this is the 10,000 runs, and the time it takes is actually quite extraordinary. It's actually quite slow to do. However, even just looking at the shape of these two graphs, we can actually immediately see that the scaling is different. However, this linear path from 64 bytes to 256 bytes is pretty much exactly the same as this part of the graph for simple init. And if you know why this is happening, why this graph becomes exactly the same just from different baselines, then please write in the comments. And obviously we talked about last time, and you can find the card in the top of the video, about 10 horrible things that developers do but shouldn't. So extending this and kind of generalizing, you need to understand that a constructor and a destructor is a function. As long as it is defined in a CPP file and it's actually non-inlineable by a compiler, it will be a function call. So those function calls, as we looked last time, are about twice as slow compared to a simple accessors through member fields, right? So avoiding function calls wherever possible and inlining our code, or making the code visible to the scope that will be using it, therefore that it can inline, is always very, very useful. Now, I prepared a different kind of a graph, which we saw before I switched it out, and that is a scaling graph. This is a scaling graph compared, for instance, simple init to constructor, deconstructor, from 4 bytes to all the way to 256. And I think what you can see that at the very small objects, because the constructor and deconstructor calls dominate the behavior and actual work, that integer writing 1 on a constructor and writing 0 to deconstructor is trivial compared to the cost of the call. Actually, these values at 4 bytes and 64 bytes are basically just dominated by these calls. However, once you move past 64 bytes, it actually is about only 2 times the performance difference between making a fully inline call and or just writing inline code generally, and using constructors and deconstructors. And again, if you know why this is happening, write in the comments below. I would be curious how much of you understand this topic in detail. That would be wonderful to know. So feel free to write it down. But of course, now I'm going to tell you why this is actually happening. Because obviously most of the architectures today have a 64-byte cache lines, and it has limited L1 caches. So here pretty much everything fits into our caches, and we can in any loop fit a lot of objects, right, into a single loop, because they're only 4 bytes of size. In that 64-byte cache line, that works beautifully. However, once we reach our limiting factor, our caches slow down slightly because you basically overfill your L1 cache. And then once you move past that, the performance kind of becomes, so the cost for caches becomes exactly the same thing if your code is in line or not in line. Now you're just paying the cost for that function call, which is about double the amount from just setting a variable to actually making a function call. So with that, I think I have provided all the information that I wanted. If you found it useful, leave that like, subscribe to this video, or subscribe to this channel, like this video. And as always, leave comments, ask questions if something's not clear, if I didn't explain why something's happening. If you disagree, just write it down and we can engage in civil conversation. And actually, I think the truth will come out. With that, now I would like to say thank you for watching again. Have a good day. I'll see you next time. Bye.